This is round 3 of supplemental stoichiometry examples. We are going to work our way up in complexity or difficulty or wording or whatever you want to say. Key ideas for stoichiometry: it's a recipe. You're working on ratios to determine how much of each reactant you need and how much stuff you can make and how much you're going to have left over. Step 1, find the limiting and excess reactant. I guess that's step 1 after completing and balancing. And I did some of the preliminary work again. We've got the molar masses for those species right there. All right. We have grams. We want to get to moles. Same deal as before. Divide by molar mass. We have 130 grams of magnesium, and we'll be a little sketchy on our sig figs here, and 100 grams of oxygen. We are going to find out what we have so that we can figure out what we need. And we need that have to be present in moles. All right, that's the basics of how this works. We are going to then divide by our molar mass for magnesium. That's coming from the periodic table, 24.31. For oxygen, 2 from the periodic table is 32.00. That's grams per mole, grams per mole. Yeah, got a little overzealous with that line. We then have 5.35 moles of magnesium and 3.12 moles of oxygen. That is the basis for our dimensional analysis. In this case, everything after the first box we need to note comes from the balanced chemical equation, right? First box is what's given. Anything after that is from the balanced chemical equation. Magnesium, magnesium 2, so 2 moles of magnesium. And I want to find out about my other reactant, compare the reactants to each other to find the limiting and excess. For every 2 moles of magnesium, there's 1 mole of oxygen. And so we end up with, in this case, 2.67 moles of oxygen that we need. And looking ahead at things, we've got more than that. So oxygen will end up our limiting reactant. But we're going to go through all these steps just because we can make use of that information later. Nothing goes to waste. Same deal here. First box is given. Everything after that from the balanced chemical equation. I have 1 oxygen, so 1 mole of oxygen for every 2 moles of magnesium. So we double that, and we end up with, following the unrounded number, 6.25 moles of magnesium that we need. All right. So if inevitably you're anything like me and you're easily distracted, you can glance at this, look away and get distracted, and look back and say, oh, I have 5 and I need 6. I don't have enough, right? So that is the one that is my limiting reactant, and we'll label it as such, limiting reactant. And this one I have too much of. That is my excess reactant, yeah? So critical information for us there, and the limiting reactant's the one that's going to determine how much product can be made. We'll get the amount excess as a little secondary step here. And it's just like going to the store and handing a clerk too much money. If you go to a store and something costs $2.67 and you hand the clerk $3.12 for some bizarre reason, they're going to give you some money back. And they're going to get that money by subtracting what you gave them, right, from what you needed to give them. So it's our have minus our need. And in this case, that's 3.12 moles of oxygen minus our 2.67 moles of oxygen. We end up with, in that case, 0.45 moles of oxygen excess, right? And we can multiply that by the molar mass and come up with our amount excess in grams. So we'll multiply by, where do I want to squeeze it in? Times 32.00 grams per mole. And we end up with 14.4 grams of O2 excess. That is not the most aesthetically pleasing way to arrange that, but we'll take it. All right, 14 grams of oxygen excess. Even if you're not asked for it, we can make use of that information later. Like I said, nothing goes to waste in these problems. So we did this. We figured out that our limiting reactant is this, our excess reactant is this. We took care of step 2 and found out how much excess reactant we have. And now we need to use the limiting reactant to find our theoretical yield. And we have 5.35 moles of that magnesium. And for every 2 moles of magnesium, I've got 2 moles of magnesium oxide, right? First box is what's given. Everything after that is what comes from the balanced chemical equation. It is a recipe for this reaction. 2 moles of magnesium for every 2 moles of magnesium oxide. Unsurprisingly, 5.35 times 2 divided by 2, 5.35 moles of MgO is our theoretical yield, right? That's moles. In lab we might be measuring in grams, so it might be useful to turn that into grams by multiplying by the molar mass, 40.31 grams per mole. And we'll end up with 215.6 grams of MgO. That is our theoretical yield. Right? So there's our excess amount, there's our theoretical yield, from which we can get a percent yield. In this particular case, we have 147 grams of magnesium oxide collected in lab, so that's our actual yield. Percent yield is supposed to be our actual, right, over our theoretical times 100. In this particular case, the actual yield is given as 147 grams of magnesium oxide, and our theoretical yield was 215. Well, 0.6. Magnesium oxide, we're going to multiply by 100, and we end up with 91.4% yield. All right? So we've got these key bits of information now. We have, well, I'll be careful with my... We have our limiting reactant, which we use to get a theoretical yield. We have our excess reaction, which we use to get an amount excess. And then we were able to get a percent yield. And now a step that isn't mandatory but should be, and that's check if you did it right. So for our check, we said the law of conservation of mass is what we're looking at. Our mass in the beginning should equal mass in the end, right? So initial mass should equal our final mass. And in this case, our initial mass is 130 plus 100 grams, right? That's our magnesium and our oxygen. And that should be equal to our final mass, which is our theoretical yield, 215.6, right? Plus our 14.4. And if you look at that, you get exactly 230, just like it was on the other side. This 215.6 is our MgO, and the 14.4 grams was our excess oxygen. All right, and so that adds up. That's good news for us. And I think that's a really useful and important step if you're going to do a little bookkeeping and not screw it up. And like I said, when I was writing a bunch of these examples, I kept screwing up. All right, that's the example number 4. Let's knock out example number 5 and we'll be done with this video. Again, these are just made up numbers. This 57 and this 80 and this 63. They're just made up. These green numbers, though, either came from the periodic table for single elements, or I added up the pieces, 2 hydrogens and 1 oxygen, 18.02. Coefficients don't come into play for molar mass, but they do come into play for stoichiometry. These coefficients give us a ratio of the things in the compound. It gives us a recipe. All right, so let's start out here with our 57.0 grams of calcium. This is an exothermic reaction. Calcium metal, when you drop it in water, actually reacts, and it kind of boils the water a bit and releases some hydrogen gas, and you get calcium hydroxide, which is only slightly soluble, so you start to get like a white goop forming in the beaker or whatever you have it in. 57 grams of calcium, 80 grams of water. And that is what we will start out with. This is single replacement. It's kind of a tricky single replacement when you see it because it's a single element and water. And one of the tricks that I recommend for that is treat that water as HOH. So then you can see, calcium might knock out that hydrogen, but it's going to leave a hydroxide behind. So just a little something to think about. I'll try and match my colors from the other side there, but I've already lost an important one. Divided by our 40.08 grams per mole, and divided by 18.02 grams per mole, we end up with 1.42 moles of calcium and 4.44 moles of water. As we are labeling things to be very careful with our bookkeeping, this is what I have. If you look, amounts that we have in moles, there they are. In fact, I said that's what we have, yeah? And we're trying to find out what we need so we can come up with our limiting reactant and our excess reactant. Everything after the first box comes from the balanced chemical equation. The first box is what was given to us. So in the balanced chemical equation, I have 1 calcium right there, right? So 1 mole of calcium is how I'm going to cancel out calciums. And I'm comparing the reactants to each other, so I need to compare to my water, and that's 2 moles of water. In this particular case, then, you're going to need 2.84 moles of water. All right, spoiler alert, we got plenty of water. Same deal here, I want water to go away. Everything after the first box comes from the balanced chemical equation. I've got 2 waters there, and I have 1 mole of calcium. We end up with 2.22 moles of calcium that we need. I've mentioned it before, but I'll mention it again. When we're comparing this 4.44, to use all of that up, we would need 2.22 moles of calcium. So that's why this is calcium here, and that's what we need to use up all that water. Over here, it's what we have of that calcium, so we're comparing diagonally. Another thing to watch out for that I see commonly is people circling on the need side the limiting reactant and the excess reactant. Don't do that. We don't need to use these numbers to find out stuff later explicitly, other than right there. We need the numbers that we have. You're more concerned with what you have. So when you go into a store, you're worried about how much money you have, not necessarily how much you need, or you're going to compare what you have. All right, anyway, have 1, need 2, don't have enough. That's our limiting reactant. And then have 4, need 2, definitely have enough. That's our excess reactant, right? It isn't critical, but again, calculating that amount excess gives us the power later to see if we did the problem correctly. So we will say amount excess is our have minus our need. And in this case, we have 4.44 of the water minus 2.84 moles of water. And so we end up with 1.60 moles of water excess. And we need to turn that into grams because grams will be a little more useful for us in the long run. But moles is fine. If you can get moles, you can get grams. We'll multiply that by the molar mass of water, which is 18.02. And that's something we calculated earlier. You end up with 28.83 grams of water excess. Now, whether or not we were asked for that, we have it. And we can use it later. That's our amount excess. So we did find our limiting and excess reactant. Excess just determines how much stuff we have left over and how much of it we have. The limiting reactant is what determines how much product we can make. So now that we know the limiting reactant, we're going to compare it to our products. And so this is slightly different than the previous examples, all of which had 1 product, yeah? And now we've got 2 products, and so that means we have 2 theoretical yields. And I'll say that again in slow-mo. This says find the theoretical yield. We have 2 products, so we're going to have 2 theoretical yields. If they specified, like if they said find the theoretical yield of calcium hydroxide, then you only need to find that one. But in general, if they just say theoretical yield, it's going to be for all the products, and that means you're going to have that many answers. And I'm going to leave a little more room when I set this one up. Our limiting reactant, the 1.42 moles of calcium, is what we're going to use to find out about those products. That's given. Everything after the first box comes from our balanced chemical equation. In this case, for every 1 mole of calcium, we have 1 mole of calcium hydroxide, and I'm actually going to change colors there. 1 mole of calcium hydroxide. And so 1.42 times 1 over 1, you end up with 1.42 moles of calcium hydroxide as a product. And I'm going to space things out a little bit here. And then we need to find out about the hydrogen gas, and we know that for every 1 mole of calcium, there's 1 mole of hydrogen gas. And that gives us 1.42 moles of hydrogen gas. So we have moles. This is our theoretical yield right here. As I said before, it'd be nice if we could turn this into grams. We'll do that by multiplying by molar mass. For calcium hydroxide, it's 74.1. I added up 1 calcium and 2 oxygens and 2 hydrogens. So we'll multiply by 74.10 grams per mole. And again, that's the molar mass of calcium hydroxide. Should give us 105.4 grams of calcium hydroxide. And then for the hydrogen, we're going to multiply by 2.02 grams per mole, and that's right there. 1 hydrogen is 1.01 from the periodic table, so 2 of them is 2.02, and that gives us 2.87 grams of hydrogen. And that right there, those are our theoretical yield. And that could be done in moles, but again, grams is going to be more convenient in a laboratory setting. So we did it. This is our limiting reactant and our excess reactant. We used this to get our amount excess, and now we found our theoretical yield. That's how much stuff we could have made, right? What we started with, how much was left over, what we made, and now we're going to get a percent yield for better or worse. To calculate our percent yield, we're going to take a look at our actual yield, which is given, and compare it to our theoretical yield. Now, I obviously made a poor choice in planning this problem out, so I'm going to change things ever so slightly and call this 0.630 grams, and we'll call this of our gas. All right? This calcium hydroxide isn't super soluble, and it does precipitate when you do the reaction. We do make hydrogen gas, but I don't know why I wrote precipitate when I originally wrote the problem. But anyway, we have changed it ever so slightly, and that's what we have now. 0.630, and it's the gas. All right, we know how to calculate our percent yield, and we'll do that by taking our theoretical yield and putting it in the denominator. We've got our actual yield in the numerator, and we'll multiply by 100. In this case, our actual yield was 0.630 grams, and our theoretical yield was 2.87 grams. And multiply by 100, giving us 22% yield approximately. We can do a little bit more with that, and I think it's important for us to do so, just so we can kind of see how things work out. Something that's not immediately obvious is the fact that this percent yield applies to all of the products. All right, 22% of the hydrogen that could have been produced was produced. Proportionally, 22% of the calcium hydroxide that could have been produced was produced because they came from the same place with a specific ratio. So this applies to all products, and we could use that to find out about our other product. And I didn't ask for it here, but we can mention it as a side note here. Find the actual yield of the calcium hydroxide. And there's a couple different ways we can do that. The first way is to utilize this percent. And a strategy that I often use in class is people get stuck. That's understandable. Step 1, when you get stuck, panic. Step 2, when you get stuck, if you can, write the equation, use it as a checklist, and then solve accordingly. So we've got a couple options here. The first of which is to abuse percent technology. The percent yield is supposed to be the actual over the theoretical times 100, right? Well, we know the percent yield because we just got it, and that applies to all products. We want to know an actual yield. We know what 100 is, and we happen to know our theoretical yield of that calcium hydroxide. All right? So we can rearrange that and find out that the actual yield is going to be the percent over 100 times the theoretical. And in this case, that's going to be 22 over 100, or 0.22, I would cut out the middleman there, times our 105.4 grams of calcium hydroxide. That gives us about 23.2 grams of our calcium hydroxide as our actual yield. All right, so that was option number 1, using our percents. Option number 2 is a little bit more work in this case, but it makes a little more sense using ratios and dimensional analysis and things like that. In option number 2, you're going to use our mole ratio, right? This balanced chemical equation gives you a mole ratio, so we're going to get moles of our hydrogen, and then we're going to use it to get moles of our calcium hydroxide. And the moles of our hydrogen that we're concerned with is that 0.630 grams. So 0.630 grams of hydrogen, that's what we actually got, divided by 2.02 grams per mole. And that gives us about 311 moles of hydrogen. And the reason we care is because for every 1 mole of hydrogen, there's 1 mole of calcium hydroxide. So we end up with 0.311 moles of calcium hydroxide. We're not there yet, but we're pretty close. I can multiply by the molar mass, which is 74.1, from right there, and we actually get the same answer, or very close within our sig figs. So we've got options there. It doesn't really matter, but knowing this key idea, knowing the percent yield of one thing, you know the percent yield of all the products, and you can then turn actual yields into percent yields as much as you want. I did not leave myself much room to check things, so I'll just try and partition this off. The mass we start with should be equal to the mass we end up with, so 57.0 grams plus 80 grams, and that was our calcium, and our water should be equal to what we made, which is 105.4 grams plus 2.87 grams. That's our theoretical yield of calcium hydroxide and hydrogen gas, plus whatever we had left over, which is the 28.83 grams that we had excess, right? And the 57 and 80 gives you 137, and the 105.4 and the 2.8 and the 28.8 gives you right around that same number, 137. So we have that checked off, and we've completed our first example problem that has 2 products, and the idea of calculating another actual yield. Once again, key ideas here. We have to have our limiting reactant so that we can come up with a theoretical yield, and there were 2 of them in this case. And we have to use our excess reactant to find some amount excess. And now we've added a step, and that is getting this other actual yield. So, and we got our percent yield along the way as well. That is the end of example 5, and we'll continue more in another video.